Okay, so today we're going to discuss ions and the charge pattern of the periodic table. So a couple of definitions before we jump in and look at this. So an ion in chemistry is any species with a charge. The reason I say species instead of atom is it could be a molecule, as in your polyatomic ions, or it could be a single atom. So we have a term cation, okay, and it's pronounced cation, not cation. I hear that tried to be read as that quite often. So a cation is an ion, as you could guess, with a positive charge. Okay. It could be any positive charge. It could be +1, +2, +3, any type of positive charge there. Then an anion, not an anion, okay, or not an onion as well, is an ion with a negative charge. Okay. So they could be -1, -2, -3. So if we think about neutral atoms, so neutral atoms have an equal number of protons and electrons. So ions have to have unbalanced protons and neutrons. So we'll just say unbalanced. We'll say number of protons and electrons. Because if the number of protons and electrons were equal, there would be no charge. So cations have more protons than electrons. Okay? So we know that atoms can't exchange their number of protons, because if they give away or take a proton, they're no longer that element anymore. So all ions are formed through transfers of electrons. So cations are formed, so we'll say formed, by losing electrons. Okay, so if you have a balanced number of protons and electrons, then you lose an electron or some electrons, then you have an overall positive charge because you have more protons than you do electrons. So anions have more electrons than protons. So notice I haven't mentioned neutrons because neutrons are neutral, so they don't really have any effect here. So anions are formed by gaining electrons. Okay. So now we want to look at how to determine if a cation or an anion will be formed by a specific atom. Okay. So I just listed out, and they're listed on your notes as well, the elements across the second period of the periodic table. So we could list the group number. Lithium is in group 1A, beryllium is in 2A, boron's 3A, carbon's 4A, nitrogen's 5A, oxygen's 6A, fluorine is 7A, neon is 8A. Also, hopefully at this point you're pretty confident with your elements and their symbols. The one common mistake that I do see repeatedly is listing fluorine as Fl. Okay, don't do that. Some periodic tables actually have an element down in this area, Fl, that's flavorium, so don't ever try and use that. Okay, fluorine is just F. But anyway, so now let's go ahead and write the electron configuration for each of these atoms here. So lithium is 1s2, 2s1, beryllium is 1s2, 2s2, boron is 1s2, 2s2, 2p1, 1s2, 2s2, 2p2, 1s2, 2s2, 2p3. So hopefully you see as you go across the period you just add one electron each time. So oxygen is 1s2, 2s2, 2p4, fluorine is 1s2, 2s2, 2p5, and neon is 1s2, 2s2, 2p6. Okay? So now I want to look at the number of valence electrons. So the valence electrons are the electrons in the outer energy region. Okay, so they're the ones furthest from the nucleus. So they are the second energy level here that we want to look at. Okay. So the first energy level is completely encapsulated by the second energy level in all these. So if you think back to the oversimplified model that Bohr had, okay, this isn't really accurate, we know that, but we can still think about it as all these electrons that we're discussing fall in the second energy level. All these have a first energy level that is full. The 1s sublevel is all full here. So lithium has 1 valence electron, beryllium has 2, boron has 3, carbon has 4, nitrogen has 5, oxygen has 6, fluorine has 7, neon has 8. Okay? So you've learned probably in physical science classes that 8 is the magic number that that atoms want to achieve as far as their number of valence electrons go. So that's true in the second period. As you go down the table, that's not quite so true. So we don't want to learn that magic number 8 as a hard and fast rule. We more want to think about what does this element have to do to get a full outer sublevel. Okay, that's what it wants to do, or full outer energy level. Okay, then they'll be most energetically stable. So all of these elements want to transfer electrons by either gaining or losing electrons in order to have a full outer energy level. So let's just go through them one at a time. So lithium has a 2s1 outer energy level. Okay? So in order to fill up the second energy level, it would have to be 2s2, 2p6. Okay? So it would need to add 7 electrons to fill up its outer energy level. So I can say plus 7 electrons, or you could lose 1 electron. Because if you lose that 2s1 electron, now the first energy level is your outer energy level, and it's already full. So it's a lot easier for lithium to lose 1 electron than it is for it to gain 7. So that's what it does. So if lithium loses 1 electron, it then has a plus 1 charge. Okay? So it lost 1 electron, but its ionic form, it has a plus 1 charge. So beryllium, in order to fill up its second energy level, would have to add a 2p6 sublevel, have to add 6 electrons. So it can either gain 6 or it can lose 2 there. Okay? So you can probably guess that it prefers to lose 2. Okay? So if it loses 2 electrons, it has a plus 2 charge, because you start off with an equal number of protons and neutrons. So beryllium here would have 4 electrons and 4 protons. If it lost 2 electrons, it now has 4 protons and 2 electrons, so an overall plus 2 charge. Beryllium, the same case. We can either add 5 or lose 3. So it would like to lose 3. That's easier. But then we get to carbon. Carbon can either add 4 to fill up its valence shell, so it would be 1s2, 2s2, 2p6 if it added 4, or it could lose 4, and it would have a full outer 1s2 shell. So that's a little bit tricky. So it turns out carbon really doesn't form an ion. Okay, so carbon rarely has a charge. Carbon is a very complex atom. So if you've heard people discuss organic chemistry before, organic chemistry is a college course that deals with the study of carbon. Okay, so there are many classes dedicated just to that atom. So for the most part, we'll leave group 4A alone when it comes to their charges. So let's look down here at nitrogen. Nitrogen could either gain 3 electrons to have a 1s2, 2s2, 3p6, or it could lose 5 electrons. So at this point, it would rather gain 3. Okay, so it can add 3 or lose 5. It's easier to add 3 here. So if you add 3 electrons, you then have a negative 3 charge. So you probably see the pattern here. Oxygen can either add 2 or lose 6. It would rather add 2 to have a negative 2 charge. Fluorine can either add 1 or lose 7. So it prefers to add 1 and have a negative 1 charge. And neon's already full. Okay, it has 2s2, 2p6. It's already good. So it doesn't form an ion. Okay, there's no need for neon to gain or lose an electron here. So now, if I were to rewrite, okay, all of these species after they formed an ion, so I'll go ahead and list these out down here. Lithium, beryllium, boron. I'm going to skip carbon because we didn't deal with carbon. Nitrogen, oxygen, fluorine, neon. So I could write plus, I could write 2 plus, 3 plus, 3 minus, 2 minus, 1 minus. And note if I mentioned it, it's perfectly okay to write lithium plus 1, lithium 1 plus. All those are equivalent notations. So if I wrote the electron configurations for these species, I can see that lithium plus is just 1s2. Beryllium 2 plus is 1s2. Boron plus 3 is 1s2. Nitrogen with a negative 3 charge is 1s2, 2s2, 2p6. Oxygen with a negative 2 charge is 1s2, 2s2, 2p6, 1s2, 2s2, 2p6, 1s2, 2s2, 2p6. So notice all of these have the same electron configuration, and all of these have the same electron configuration. So what's the term that we use for that? Hopefully remember it's isoelectronic. Okay. So if I were to write the electron configuration for helium right here, it would be 1s2. So we'll find that most ions, okay, prefer to have an electron configuration that is isoelectronic with a noble gas. Okay, so helium and neon are noble gases. Noble gases are very stable. They don't like to react. Okay, they're the most stable form of themselves. So atoms like to have electron configurations that are isoelectronic with these noble gases because they're so stable. Okay, so you'll see that quite often. So now let's look at the periodic table and think, well, what can I do with this information now? Okay, that was a lot of work to figure out the charge of oxygen. I don't want to do that every time I go to the periodic table. So if we look at the periodic table, let's look at 1A, where lithium falls. So it turns out the whole 1A column behaves the same. This doesn't mean that the 1A column always has a +1 charge. This means if the 1A column forms an ion, its charge is +1. Okay, so you can have neutral lithium. Okay, you can have neutral sodium, but if that sodium has a charge, it's going to get that charge by losing 1 electron and becoming +1. So you'll never have +2 sodium. It'll always be +1. The alkaline earth metals, okay, form a +2 charge. Okay. The transition metals, we said they have variable charges, so we don't really deal with them in this course. When we work with them, their charge will be given to you. You won't have to determine it. Okay. Boron is a little bit different. It wasn't a great example. It's a metalloid. But if you think about the metals below boron, they will form +3 charges. We skip the carbon column. The nitrogen family forms -3 charges. The oxygen family -2. The halogens form a -1 charge. And the noble gases don't form a charge. Okay? So this is the charge pattern we call across the main block of the periodic table. +1, +2, +3, skip, -3, -2, -1. We don't worry about it. So if I ask you, what is the charge of a selenium ion? You could look at selenium, -2. Okay. You can write this on your table for now, but eventually you'll need to know these by heart. We'll use this enough that you should have this pattern memorized. So if I ask you, is a calcium ion a cation or an anion? You can say, well, calcium has a +2 charge when it forms an ion, so I know positive charges are cations. Okay, so hopefully this made sense. Okay, and we understood why we have these charges, but we don't go through this every day. Okay, we use this kind of as an example to show why this charge pattern holds. What we'll do is just use this charge pattern, okay, to determine what the charge of a specific atom that we deal with is. So if you'll notice, if I cover up this section, everything that I've shown is either a metal or a metalloid, okay? And they all have positive charges here. So it turns out metals almost primarily form cations, so you won't really see a metal with a negative charge here. Just something to watch out for. So if you forget how the pattern goes, you can remember, well, the metals always form a positive charge, so I need to start with the positive, +1, +2, +3, okay?